Welcome to Homework 8, Problems 2.6-1 and 16. A steel bar of rectangular cross-section carries a tensile load. The allowable stresses in tension and shear are 14.5 and 7.1 kips per square inch, respectively. Determine the maximum permissible load. So we know our generic equation for sigma is force over area, and in this case, we're not doing any force over some shearing area, but instead we want to know the shear due to a tensile force. It's just simply due to the fact that you can rotate what perspective we're viewing shear from, and thus we acquire a shear from a unidirectional tensile or tension. And the reason we have sigma halves is because we're looking at the max shear, and if you plot tau as a function of sigma, which is negative sigma cosine theta sine theta, then you'll get your maximum at 45 degrees with a magnitude of sigma halves. That's where that comes from. So we're looking for a maximum force, and we can solve for that force because sigma is a function of f, so is tau because tau is a function of sigma, which is a function of f, and we can rewrite it with terms of our force. And then plug and chug with their values from the problem statement, and we'll see that 42.6 kips will be the maximum force that our member can tolerate. Two boards are joined by gluing along a scarf joint, as shown in the figure. For purposes of cutting and gluing, the angle alpha between the plane of the joint and faces of the board must be between 10 and 40 degrees. Under a tensile load, the normal stress in the boards is nearly 5 megapascals. If our glue joint is at 20 degrees, what are the normal and shear stresses? So we have an equation for normal and shear stresses, which is this. However, for this equation, theta is from the vertical, so we're going to want to subtract our alpha from our theta before plugging everything and getting our answers. If the allowable shear stress on the joint is 2.25 megapascals, what is the largest permissible value of the angle alpha? So right here it's talking about shear, so we're going to be using this equation and setting it equal to our shear. However, you'll notice it will be very difficult to find theta, considering that we have two trigonometric equations that theta is inside of. But also thanks to trig, we know that sine theta cosine theta is half sine 2 theta, or if we didn't know that, now you know that. Or you could probably go use some other method to try to make there only be one method. This is the one I chose. And then when we have this knowledge, then we can solve for theta as a function of sigma. And so, quick note before you plug that into your calculator, I just want to show you something really important with trigonometric functions. So this is a sine curve, and you'll notice that if you're going to plug this in, and your magnitude that you're doing an arc sine of is going to be roughly at that y value that I've drawn, it is going to spit out 66.6 and then of course 33.3 because you're actually plugging half of that. So if you use that value, you are cutting yourself short. You won't be, there's a possibility that you'll be right and there's a possibility that you'll be wrong, and here's why. If you look at the height of my little dash there, and you continue to the right, you'll notice that there's a second location that it could have gone to, and that would be roughly 113-ish, something like that. And since we're taking a half of it and the whole thing goes to 180, you can take half of 180, which is 90, take 90 and subtract your theta that your calculator output to get 56.6. So 33 1/3 and 56 2/3 are the two values that your theta could be. However, your calculator will only show one because with arc trigonometric functions, it will only show the first result because your calculator can only give one answer unless it's super fancy. So we have to look at both of these. Now, also recall that alpha is theta minus 90. So we're going to do that to both of our values, and we're going to get 56.6 and 33.3. That didn't do too much different for us, but that's just for technicalities, just to make sure that we're not doing something incorrect. And recall in the problem statement that it said alpha must be between 10 degrees and 40 degrees. And this is the crucial part. This is what's telling us, okay, only one of these answers is correct. We can't use the 56.61, which is what you would have used if you had just gone through with where your calculator spat out, because it would have said 33.3 degrees, and then you would have subtracted that from 90. So it looks like I have my equation backwards. And then you would have gotten 56 degrees, and that's not within 10 to 40. And so this is why this is important to recognize. Then, for what angle alpha will the shear stress on the glue joint be numerically equal to twice the normal stress on the joint? So, we know that tau is going to be 2 sigma, alpha is 90 minus theta, and we also have these relationships. So if we're going to set one of them equal to double the other, do some algebra here, we're going to find that tangent of theta equals 2 if you do arctangent of that, and then of course 90 minus that because we want alpha, not theta, then you're going to get 26.6 degrees. Alright, concepts and equations for inclined stresses. So, what we've been looking at is just a typical boring beam with an axial force. And if we are to graph the shear force going through this beam, it is equal to 0, just because it's completely axial, so it's very boring. However, if we rotate our beam, then from some x-axis, which is labeled as n here, then we do have some shear force, and it will be this P times sine theta. And that's because if you take your vertical element of this P, then that's your shear. And so it is no longer 0. And since your horizontal is remaining, that is going to be affecting your normal stress for some orientation. We're not talking, because again, if you had it normal and flat, your normal stress is going to be different. But for some specific orientation, your stresses are now going to be, your forces are going to be that horizontal component. Since our stresses are functions of forces in particular directions, we now have our shear and normal forces with respect to a new area. And our new area is our original area divided by cosine theta. So when we put everything together, we get the equations that we all know and love, or possibly hate, however you see it. And that's what's happening here. And those two equations at the bottom are pretty much the only thing you need to know from this. But everything prior, that was the derivation, that was just to help you hopefully understand why this is the case and why we even have a shear for a strictly axial force. And it has everything to do with the fact that we have some infinitesimal element in our plane. We're rotating it because there's still forces in every direction, and it's really complicated and stuff, and we want to see, okay, from some orientation, what else can we know of what's going on?